All right, so any questions? Is that a question or?
I think so.
Okay.
I don't have my homework to reference it anymore, but it was the last section, like the ones where we had to find the factorization with the squares in it.
Oh, like 7a, b, and
Let's see.
Yeah, that one.
I think they go over that once yesterday, but like not in depth.
So 5 point, something like 5.5 maybe?
It was 5.7.
5.7 modular arithmetic.
Yeah, it was 5.7.
Yeah, modulo over 7.
All right.
Riverside 7, right? Yeah.
7, 8, find the value of 4 to the 45th and Z11.
Yeah, I couldn't figure out how to do A.
Yeah.
But he's asking about B.
Well, let's see. Everybody turn this in, right? Okay. So find the value of 4 to the 45th. And when it says in Z11, that means mod 11. This funny symbol, Z11, that's what we call the ring of integers modulo 11. So it's just the numbers 0 through 10. So find 4 to the 45th in Z11. A is using the fact that 45 equals 3 times 3 times 5. And B is with repeated squaring. Not repeated swearing. Well, 4 to the 45th is equal to 4 to the 3 times 3 times 5. Which I think would be 4 to the 3rd to the 3rd to the 5th. Right, good old exponents. And so if we're working mod 11, 4 is congruent to 1. 4 squared is 16, which is 5. 4 cubed is 64, which is 55, 9. It's also 5 times 4, which is 20. Which is congruent to 9. So 4 cubed is congruent to 9 cubed. And I'm going to get lazy and say that 9 is congruent to -2, so this is -2 cubed, which is -8, x, which is also +3. And so 4 cubed to the 5th is congruent to 3 to the 5th, which is 3, 9, 27, 81, 243. And what's 243 divided by 11? I don't know. So 11 times 22 is 242, so this is congruent to 1. Thank you. But I'm guessing there's maybe an easier way we could have done this, which was 4 to the 45th is equal to 4 to the 5th to the 3rd to the 3rd. So we found 4 to the 3rd was 9, which is -2. 4 to the 4th is -8, which is 3. 4 to the 5th is 12, which is congruent to 1. And if you happen to do this first, now 4 to the 5th cubed is just 1 cubed, 4 to the 5th cubed is just 1 cubed again, which is just 1. That'll get you to 1 without having to do these bigger numbers. So that's one approach, but the other suggestion is to use repeated squaring. Yeah, so this is the breaking the thing into binary that we did. So 4 squared, 4 to the first is just 4. 4 squared is 16, which is 5. 4 to the fourth is this thing squared, which is 25, which is also congruent to 3. 4 to the eighth is 9, which is also negative 2. 4 to the 16th will be negative 2 squared, which is 4. 4 to the 32nd will be 16, which is 5. And that's as far as we have to go. And now you can say 4 to the 45th is equal 4 to the 32 plus, and we're writing 45 in binary now. So 32, 42, 5, that's an extra 13, so it's 8 plus 4 plus 1. And now law of exponents says we multiply these. And modular arithmetic says this is congruent to whatever each of these is congruent to, all multiplied. So this is 5 times 4 to the eighth is 9, 4 to the fourth is 3, and 4 to the first is 4. So 45 times 12. 12 is congruent to 1, so that's 45 times 1, and 45 is 1 more than 44. So that gets you to 1 also. So different ways to approach this. All right, other questions?
Prime factorization. I don't remember what problem it was, but other than just trial and error.
I think it's 5.8.
It's mostly trial and error.
Yeah, you're still gonna like remember them.
So find the prime power factorization of these integers.
Yeah.
Yeah, purely trial and error.
I think D was the one that took long.
Let's take a nasty one. So 1662405. So pull up your favorite calculator. And I always go after just BC-L, which is like infinite numbers of digits. And we know this number is going to be divisible by 5 because it's got a 5 on the end, right? So let's start with that. 1662405 divided by 5. And that's going to give us 332481. And if you add up the digits, that's a multiple of 3. So that's going to be divisible by 3. And if you add up these digits, that's going to be divisible by 3. And if you add up these digits, that's going to be divisible by 3. And that does not work. So it's 5 times 3 cubed times 12314. Is it? Let's see.
Is the second division by 3 is one number?
Oh, you're right. Yeah. Okay. All right, times 110827. So it's not a multiple of 11.
Should be a 3, though, isn't it?
Say what?
No. No, it's not. It ends being 1. See, I've learned to
Yeah, we're
start
good
with
so
the
far.
small numbers. And
Right.
The small primes, and so I can cancel primes out,
Mm-hmm.
Because if I find that one number is divisible by 2, every other factor is also not divisible by 2.
Right, right.
And so if I do 2, 3, 5, and then I come to another stop later, I don't have to do those. I can skip to 12.
That makes sense, yeah.
One of the questions I had to do, like, it was divisible by 19, but none of the other primes.
Right, yeah, so this one's divisible by 19. So it's trial and error. So 3 times 5 times 19 times 5833. And who knows about 5833?
I had to like list the primes out.
19 again. That's pretty cool.
And then I think 307 is fine.
Times 307. And yeah, we're already above. Whoa. Thought you could take square roots. Oh yeah, you can. Okay, we're already above the square root. Yeah, so there's your prime factorization. And yeah, purely trial and error. Factoring is a hard thing in general, right? It's the key to things like public key crypto systems. Really hard to factor, especially if the factors are big primes. If you've got lots of multiples of 2, then it's not too bad. You can shrink your number down pretty quickly. Most numbers, well, a third of the numbers are divisible by 3. So that usually works out. This is a fun question. Richard orders a pizza every 10 days and has dinner with his parents every 25 days. If he has pizza for lunch and dinner with his parents today, when will he do the same again? So how often does he end up having a pizza and dinner with his parents on the same day? So pizza every 10 days, dinner every 25, and Jeff said every 50. So why is it every 50?
Multiple of 25.
Yeah, it's a multiple of both of these. Whatever this period is, if it's a multiple of the number of days over which he eats pizza, then he's going to eat pizza on that day. And it's also a multiple of the number of days between dinners, and so he's going to eat dinner that day. This is also a valid answer. This is also a valid answer, but this is the least common multiple. And least common multiple is related to greatest common factor. So what if he had pizza every 11 days and he had dinner every 23 days? How long is it going to be? Assuming they have pizza and dinner today, how long is it going to be until that happens again? Yeah, because the least common multiple of these is 11 times 23. So 243. Is that what it is? 253. So this is one of the cool things about primes, right? Slightly different periods here, very different outcome. So how many people here know what cicadas are? Yeah, the bug. So these really cool looking bugs, they're about this big, they have these bright red eyes, and they pop out of the ground every 17 years, back east in particular. I don't know if you have broods out here, I haven't heard any, but they have a really existential kind of life cycle. They climb up in a tree, they mate, they climb up in a tree, they drop larvae down into the ground, the larvae burrow into the dirt, and they sit there for 17 years. And then 17 years later, they all hatch the same few days, few weeks, and they all mate and go into the ground. Another 17 years later, the same thing happens. And if you've ever been in a forest when these broods have hatched, it's incredible. It's deafening. I mean, it's really painful sound level. And just being in town, I mean, everything is covered with cicadas. The roads are disgusting because cicadas cover the roads too, but they're everywhere. And they're freaky looking, but they're pretty cool. And they do this on a 17-year cycle. And there's another brood which works on a 13-year cycle. And one of the theories for these particular periods is that they're both prime numbers. And the time between when both broods emerge during the same season is, you know, those two multiplied together, it's over 2 centuries. So it minimizes competition, things like that. So these things pop up in the weirdest places, which is kind of cool. All right, any other questions? So let's start with Fermat's little theorem. And this was a theorem Fermat actually proved. So if P is a prime, and A is not a multiple of P. If A is a multiple of P, then the statement is silly and it's not true. But if A is not a multiple of P, then A to the P minus 1 is congruent to 1 modulo P. So if you have a prime number and you have a reasonable number A, and you raise it to the P minus 1, it's exactly one more than a multiple of P. And this only works if P is prime, but let me see, how does this work? There's a one-way conditional here. You can't use this to test primes. Okay, there's non-primes for which this will be true. But if P is prime, this is guaranteed to be true. All right, so who cares? Well, this is another trick we can use, like modular exponentiation, to calculate large exponents of numbers modulo a prime. So here's an example. So let's calculate 7 to the that's a good example. Let's calculate 7 to the 221st modulo 11. Now multiplying 7 by itself 220 times is not what we want to do. And modular exponentiation will still require us to do about 8 multiplications. 7 to get up to 7 to the 128th, and then a bunch of multiplications to add up those exponents. But we can use Fermat's little theorem as follows. So we know that 7 is not a multiple of 11. 11 is prime. So by Fermat's little theorem, we know that 7 to the 10th is congruent to 1. p is 11, p minus 1 is 10. So 7 to the 10th is congruent to 1. And 1 is a nice number because we can take exponents of 1 and we still get 1. So we can observe that 7 to the 220th is equal to 7 to the 22 times 10, which is equal to 7 to the 10th raised to the 22nd. And since 7 to the 10th is congruent to 1, this is congruent to 1 raised to the 22nd, which is just 1. So without really doing any work, we've already found what 7 to the 220th is. In fact, 7 to any power that's a multiple of 10 will be exactly 1. And so since we want 7 to the 221st, that's just 7 to the 220th times 7, which is congruent to 7 to the 220th is 1. 7 is congruent to 1. That's congruent to 7. So there's 2 to the 221st. There's 2 to the 221st minus 7. And if we divide by 11, we get an integer. We don't get an integer. Uh-oh. I did 2 to the 221st. Should have done 7. The heck am I doing here? Yeah. So 7 to the 221st minus 7 divided by 11. That's an integer.
It's cool how it does the backslash. Just makes me think you're supposed to type this into something else.
Yeah, so I think you can do backslashes on input. So you could take the output and feed that back into BC. Yeah, that's a nice feature.
You could also feed it into a C program, right, for just copying and pasting.
Mm-hmm.
That's what it's for.
Yeah, so 1 year for 215 for your programming assignment, this is when I did 3 programming assignments. I had people write something like BC that would do theoretically unlimited precision calculations. And it's a fun thing to do. It's good. It's a good C practice problem. It's really just using arrays and some logic. You don't have to get into a whole lot of fancy mechanisms. But BC's cool. All right, so that's Fermat's little theorem, and we can apply it in all kinds of situations. So I don't know, let's just pick a number, 15 to the, what should we work, mod 7? So 15 to the 7,000th, mod 7, which is a ridiculous number. Well, we know 15 to the 6th is congruent to 1. Mod 7. So how many times can 6 go into 7,000? So it looks like 1,116. Plus a little bit left over.
46.
Is it 4?
It's 1,
66.
The heck am I doing?
7,000.
66, that's what you meant. Okay, plus 4. So 15 to the 7,000th is actually 15 to the 1166 times 6 plus 4, which is 15 to the 1166 times 6 times 15 to the 4th, which is 15 to the 6th raised to the 1166 times 15 to the 4th. And since 15 to the 6th is congruent to 1, this is just 1 to the 1166, so this is congruent to 1 times 15 to the 4th. So we know that this is congruent to this. So let's just take a problem with a ridiculously large exponent and reduce it to a problem with a much smaller exponent. And in this case, 15, well, this was a silly exercise because 15 is congruent to 1. So we didn't even need to do this, but ignore that, right? We could just take 15, find what it is, mod 7, raise that to the 4th. But I picked a silly example because 15 is already congruent to 1. So mod 7, that should be an integer, yeah.
Yeah, my 89 integer on the 4 tried to do it.
Yeah, yeah.
Yeah, I'm doing logic print mod 7. It's giving logic value 7.
Mm-hmm. BC is nice. Yeah, it doesn't do factorials. Well, it probably does, but not that way. All right, so cool on Fermat's last theorem. Did I have a homework question on that?
No?
Okay, I should have, except that I didn't go over it. Yeah, Fermat's little theorem, not last theorem. Yeah. I don't think there is one. In fact, I was reading about where this theorem got named the little theorem, and nobody's really sure. But it was probably in the shadow of Fermat's last theorem. Yeah, yeah. That one seemed to work well. So applications. Lots of applications for modular arithmetic and number theoretic things. One simple application is something we call parity. So what's the idea of parity? So not too long ago, when you wanted to talk to a computer remotely, you used a telephone. And you had this thing called an acoustic coupler. And you'd pick up your phone, you'd dial the number of the computer. It would answer, it would make a whistling sound, and you would take the handset and you'd put it down in this contraption, right? This acoustic coupler. And it allowed your computer to send tones over the phone and to receive tones from the phone. And that's how information was sent to and from a remote computer. You've probably seen these in bad movies.
Something like speakers use?
Yeah, yeah. So you used to be able to whistle into a phone when you called up a computer and compel it to do different things.
The story of the one guy who was like, no, different story. He memorized a ton of the things and he was able to whistle to them.
Yeah, yeah. There was a famous phreaker called Captain Crunch. He passed away about, I don't know, several years ago. But he was named Captain Crunch because he discovered that the whistle that you got for free in certain boxes of Captain Crunch used the right frequency to trigger certain activities on AT&T's phone network. And he used that to like do some phone phreaking. So yeah, that's an acoustic coupler. I've actually used this particular one. And you just stuff the handset down in there. It doesn't work with cell phones very well, right?
Similar thing to those noisy modems?
Yeah, so you find this in like techno music and stuff, the squawking sounds that you get. And it's inherently error prone, right? So these pieces of rubber around here were intended to make an airtight seal so that outside noises wouldn't get into the phone and confuse the computer. But if there was a loud noise, it would get misinterpreted as signals to or from the computer, and that would cause transmission errors. And of course, if someone picks up the other phone in the house, then all bets are off. So here's the problem with that. You're sending information to a computer, and you're transmitting grades, right? So you're entering grades for a student, and here's the ASCII code for an A. Okay, this is 65, which is an A. And you send this out 1 bit at a time, and you use a high tone for a 0 and a low tone for a 1, for example. So you alternate between 2 pitches, and depending on the pitch, it gets interpreted as a 1 or a 0. So you send out the right tone to signal a 1, and the computer receives that. And now you send out a different tone to receive a 0, but a cat freaks out and makes a loud meow in the background, and this gets interpreted as a 1. And then you send out the 0, 0, 0, 0, 1, 0, and what the computer has received looks like a 67, which is the ASCII code for a C. So I entered in your A into the computer at school, but it thinks that I typed in a C, right? So how do we know that this happened? And in general, you don't. So one idea that was used early in this kind of system was to add an extra bit over here called a parity bit. And there's 2 kinds of parity, even and odd. So let's just talk about odd parity. The idea was, before I send out this number, I count the number of 1s. And then I put an extra bit on the end, either a 1 or a 0, so that the total number of 1s is odd. So total number of 1s is odd. So I want to send out this 8-bit pattern that has 2 1s in it. I'm going to set my parity bit to a 1. Now, when I transmit this to the computer and the computer receives this, it counts how many 1s it received, including the parity bit. 1, 2, 3, 4, that's not an odd number. It knows something went wrong. And it'll send a message to me saying there's a parity error, please resend. And then I'll resend, and hopefully it gets this, and it says 1, 2, 3, that's odd. Okay, that's a good character. So it's an error check, a very rudimentary error check. But it worked pretty well. And it will pick up a single bit error, including if there's an error in the parity bit. If I meant to send a 1 and I send a 0, that'll trigger a parity error also. But the 2 downsides are, 1, it doesn't pick up multiple errors. If I send something like this, there's still an odd number of 1s, it's going to think that that's perfectly fine, and you're going to get a grade of a G, whatever that is, good. The other problem is, if you know there's an error, it doesn't help you correct it. All you can do is say, wait a minute, something went wrong, say what you just said again. But it's a first order method, okay? So how do we do this? Well, basically, just take the sum of the bits and then add 1 and reduce it modulo 2. So that's for odd parity. If you just do the sum of the bits and reduce mod 2, that gives you even parity. The disadvantage of even parity is if something goes wrong and you just keep sending out zeros, that looks like perfectly fine zeros. Because if I actually wanted to send a 0, I'd put the parity bit to be a 0, and it looks like I'm sending a valid character. With odd parity, if I want to send a 0, this is what I have to actually transmit. And if something's wrong, if my line is dead and I'm just sending out zeros repeatedly, it'll at least trigger a parity error. But different reasons for using these. So that works well for slow communication. Well, you just want to know pass or no pass, right? Is this a good piece of data or not? But in computers, memories in particular, memories tend to be error prone. The voltages being used are very small. The physical geometries of the cells storing our information are very small. And things like stray alpha particles coming from space will perturb the bits stored in memory. So good memory uses something like ECC, error checking and correcting. And it's like parity, but it's a more complex formula. It's still a calculation that you do modulo something else. But if you have 3 parity bits, 3 ECC bits on a 32-bit number, you can detect something like 3 bit flips, and you can correct either 1 or 2 bit flips. So it doesn't just tell you something went wrong, it actually lets you figure out where the bit is that's incorrect and put it back to its correct value. And so this is what error checking and correcting memory is used. All right, we're talking about hash functions in CSE 222. That's another application of some of this modular arithmetic, right? Because we use that in our hash functions because we're trying to map into a table with a certain size. And the theories about what's a good table size, should our table hold 10 things or should it hold 11 things? 11's better because it's prime. That's all number theory related. Let me mention 2 other applications. One is universal pricing codes. So, shockingly, I may not have anything on my person with a UPC code. Who's got something with a UPC code on it?
Yeah, kind of.
Here we go.
Okay.
Papers on this thing.
All right, thank you. That's an ISBN code, but that'll work because we can also do ISBNs. So UPC codes are, you know, those pricing things that you have when you buy something at the store. ISBNs are similar. It's a barcode, and it identifies a particular book, actually a particular edition of a particular book. So let's just play with this code. So 9781423201908. I may not have the algorithm for this type of ISBN. Yeah, let's do that because this is. All right, thank you. All right, so UPC code. So we have 26229-77076, and we have an N number of 0. Let me see your eraser.
Oh, sure.
Something that's non-zero. Zeros are kind of. But anyway, okay, so here's what?
This is a 6.
Is a 6 check digit?
Yeah.
All right, what's the whole number?
0, 7, 0, or 972. 112. 476.
All right. All right. So here's the idea. You can make a barcode by just filling in, you know, with a Sharpie what the different lines are, right? And if you go into a store with a Sharpie, theoretically, you might change the UPC code of a TV set to the code of an eraser. And when they ring it up over the check register, it says, you know, 79 cents. And, wow, that's a good deal. And you pay the 79 cents, tell them to keep the change, and you take off, right? So one way to help prevent that is that not all UPC codes are valid. Okay, there's check digits built in, and I believe it's this last digit that's the actual check digit. And this happens with credit cards too. You can't just type a random 16-digit number in for a credit card and have it accept it. There's only certain 16-digit numbers that will actually register as a valid Visa or a valid MasterCard. and there's an algorithm to look at the 16 digits and know whether or not it's valid. So the same thing with UPC codes. So here's the algorithm for UPCs. It's an 11-digit code. So if we take 3 times the first digit, plus the second digit, plus 3 times the third, plus the fourth, plus the 10th, plus 3 times the 11th, and we reduce that modulo 10, and if it's not equal to 0, subtract from 10. All right, so the other way to think of this is just take the odd position numbers, add them together, multiply by 3. Take the even position numbers, add those together. Add those two sums together, reduce mod 10, and if you get something different from 0, subtract from 10. So let's try it with this one. So let's find our odd digit position. So it's 0, 0, 7, 1, 2, and 7. So add those together, 7, 14, 17, and then multiply by 3 is 51. So that's the sum of the odd digits. And then the even digits, 7, 9, 2, 1, and 4. So 9 and 7, 16, 18, 19, 23. And then 51 plus 23 is 74, mod 10. This is congruent to 4. 4 is not equal to 0. Subtract it from 10, gives you a 6. That's what your check digit should be. So that's a valid UPC code. And if we do this over here, presumably 3 times the odd plus the evens will turn out to be a multiple of 10. So when we reduce mod 10, we'll get 0, and we'll just leave the check digit as 0. Okay, why do we do this? Well, number one, this will pick up 100% of the errors where you have an error in a number. If any of these numbers change, you're guaranteed to get a different check digit. And when you check your validity, it'll say, no, the check digit isn't right, something's wrong. But it'll also pick up 90% of the transpositions. So before laser scanners, you had to type these codes in. And probably the most common key punching error is to transpose 2 digits. So you type in a 2 and a 7 instead of a 7 and a 2. And this will pick up 90% of all transpositions. So that's cool. ISBN uses a similar code. So this is ISBN 9, which is why I didn't want to use that book. There's a few different ISBN standards. So basically, you add up each of your digits multiplied by I. So it's a weighted sum where the weight's given by the position in the number, and you reduce this modulo 11. And so there's 10 digits you can use. There's 11 digits you can use. You can use an X, which has the value of 10. And this will pick up incorrect errors, and I think it'll pick up all transpositions of digits. So there's lots of different check codes. There's a whole theory around coding information and doing it in a way that detects errors or lets you correct errors. And it's all number theoretic related. All right, so that lets us talk tomorrow about crypto systems. So we'll talk about some very old ciphers, things like a Caesar cipher, ways to encrypt information that require you to know a password. And then we'll talk about public key crypto systems, which is what all modern e-commerce is built on top of. All right, so we'll be there tomorrow.